Hello guys, welcome to Physics Grad. In this video, we are going to see how differentials behave when we apply the Legendre transform to it. And this is the fifth part of the Legendre transform series. So let us begin. So let us start by consider a function which depends on two variables x and y, which is convex with respect to x. Okay, this would imply that the second order partial derivative of the function with respect to x must be greater than 0, greater than or equal to 0. This is the meaning when I say that f of xy is convex with respect to x. Then how do we describe the Legendre transform of this function? Okay, then f star of p comma y, okay, where p is the conjugate variable of x, okay, then this would be nothing but maximizing over some variable x dash the expression px dash minus f of x dash comma y. Okay, so this is the definition of Legendre transform. Now here I am using x dash instead of x just for notational to avoid notational confusion, because later on I want to the transformed function I want to write it in terms of x. Okay, so this would imply that dou by dou x dash of the expression px dash minus f of x dash comma y must be equal to 0. From here we get the condition that p must be equal to dou f of x dash comma y by dou x dash. Okay, therefore this implies that px dash minus f of x dash comma y will have a maxima at x dash equal to x such that p equal to dou f x dash y by dou x dash at x dash equal to x. Okay, so what are we doing? We are choosing the value of x dash as equal to x such that the partial differentiation of the function f of x dash y with respect to x dash at the value of x dash equal to x should be equal to the value of p which is chosen here. Okay, so the important thing to note here is that, okay, x dash is independent of p. X dash is independent of p. What we mean by that is that when we consider this particular function, okay, I can choose any value of x dash, but only for particular value of x dash will this expression have a maxima. Okay, therefore the choice of x dash here will not depend on the value of p chosen, whereas when we say that, so our f star here, when we choose x dash as equal to x, f star of p comma y will now become px minus f of xy, where in the expression for max of x dash px dash minus f of x dash y we have chosen the value of x dash equal to x where this condition is satisfied. Okay, so in this equation the x is dependent on p. X is dependent on p. Why? Because this is the value of x dash where px dash minus f of x dash y will have a maxima, and that value corresponds to the case where the derivative with respect to x dash of the function takes the value p. Okay, so when you evaluate dou f by dou x dash y at x dash equal to x, you will get some expression in the form of x and y. I can always write rewrite this as a function of p and y. Okay, so to understand this, let us consider an example. Let us say that f of x dash y is equal to x dash square times mod y. Okay, then the value of p is equal to dou f of x dash y by dou x dash at x dash equal to x. This is equal to 2x dash mod y at x dash equal to x. This is equal to 2x mod y. Now I can always write, okay, we can write x as equal to p by 2 mod y, which is my function depending on p and y. That is what I am writing here. Okay, so using the expression for this value at x dash equal to x, we can write x in terms of p and y. So that is why I am saying x is dependent on p, whereas we cannot write x dash in this form. Therefore x dash is independent of p. So that is why I used x dash initially, to make sure that our final result is in terms of x. Okay, so this will avoid some confusion, and that is the reason I did it. Now let us consider, okay, now consider the differentials df. Since f depends on x and y, this will be written as dou f by dou x dx plus dou f by dou y dy. These two terms say that this particular function depends on x and y. Similarly, the Legendre transform f star of p and y should depend on dou f star by dou p into dp plus dou f star by dou y dy. Okay, but this, since f star is equal to px minus f of xy, okay, this will be equal to dp into x plus x into dp minus dou f by dou x into dx minus dou f by dou y into dy. Okay, but we had seen that this particular value dou f by dou x is basically equal to p because of this relation. Okay, that is the derivative of the function at the value of x, and this is also the derivative of the function at the value of x, and both are equal to p. So this will be equal to x dp plus dp into x, I have written it like this, okay, minus p dx minus dou f by dou y dy. Okay, now since this is dependent only on dp and dy, our terms depending on dx should cancel. Oh, where is that? Oh, I have written the same term here again. So this is dx times p. Okay, so this will be dx times p. So these both will get cancelled, and finally what will be left with? X dp minus dou f by dou y dy. Okay, so comparing this with this particular expression, we see that dou f star by dou p is equal to x, and dou f star by dou y is equal to minus dou f by dou y. Also, dou f by dou x is equal to p, and the other relation dou f by dou y will be equal to minus dou f star by dou y. That is the same as this relation. Okay, so we see that the differentials, the partial derivatives, are in a way related with some form of symmetry, in the sense that dou f by dou x gives us p and dou f star by dou p gives us x. So there is some kind of a symmetry in this equation, and that is what we have to notice here. Okay, so those kinds of relations are very often used to derive the various thermodynamic potentials, which we are going to see in the future courses. Okay, and that is the thing which I wanted to highlight. And to conclude this series of videos on the Legendre transform, I want to make the following remarks or observation. Okay, usually in physics, f of x y represents some physical quantity, okay, in terms of x and y, which may in turn be some other physically varying quantities. Okay, so this may be, for example, the Lagrangian, which is expressed in the form of velocities and coordinates, where x becomes the coordinate, y becomes the velocity. That is one example, and similarly you can think of many other examples as well. Okay, so that is what I meant by saying that f of xy represents some physical quantity in terms of the variables x and y. So then, if we want to describe the same physical quantity, okay, using dou x by dou y, dou f by dou x, or dou f by dou y, or dou f by dou x and dou f by dou y, okay, then all we need to do is take the Legendre transform of this, because the Legendre transforms both are nothing but viewing the same thing but from different perspectives, as we have already seen. So taking Legendre transform of this function with respect to x or with respect to y will not change what the function is describing. Okay, so this implies f1 of p comma x defined by px minus f of xy, which is the Legendre transform of f with respect to x. Okay, we'll also describe the same physical quantity, but now in terms of p and x, where p is dou f by dou x. Okay, so remember here p can't be any value, it should be equal to dou f by dou x. And here again this x is actually, as we have seen, the value of x dash, where the expression px dash minus f of x dash y is maximized. Okay, that you should always keep in mind. This is not a direct equation, this is got by maximizing some function of x dash. Okay, so similarly f2 depending on x and v defined by vy minus f of xy, this is nothing but the Legendre transform of f with respect to y, and this also will describe the same quantity but now using the variables x and v. Okay, and similarly we can have f3 of p comma v, which is defined with defined as px plus vy minus f of xy. This is the Legendre transform of f with respect to x and y. Okay, so in general quantity described using n variables, okay, can be equally well described using 2 power n functions derived using the Legendre transform. Okay, which means if we have a function which represents some quantity which depends on physical variables x and y, okay, then I can represent the same quantity using four different functions which I can get by using Legendre transforms. And all of these four functions describe the same quantity but using different variables. Okay, so this in a way gives some kind of a relationship, and by describing the same quantity from different perspective, sometimes it makes it easier to solve the problem by introduction of some kind of symmetry which was not obvious in the beginning. Okay, so that is the use of Legendre transform, especially in physics, because often the partial derivatives or the derivative with respect to some variable often describe some other physical quantity as well, and that is why these relations is useful when we study physics, especially thermodynamics and classical mechanics. So all of these concepts are used to derive the various thermodynamic potentials, or to go from the Lagrangian formalism to Hamiltonian formalism in classical mechanics, and so on. So with that, we come to the end of our series of lectures on the Legendre transform, and yeah, thank you for watching. See you next time.